Welcome folks. In today's lesson we're going to look at a wave phenomenon, one which binds and is used in many different areas, more than we sometimes realize, and it connects the Sonic the Hedgehog character to sounds emitted from a EMS ambulance. It's also used in ultrasound therapy, in the medical world. It's used by the police force in terms of speed guns, and also in the sports arena to measure the speed of a baseball. And it's also used as a way to understand and explain the Big Bang Theory. So suffice it to say that this is a wave phenomenon that's very important. So the wave phenomenon that we're talking about is called the Doppler Effect, and the Doppler Effect is much more than dear old Sheldon Cooper's Halloween costume. It is a real effect, an actual wave phenomenon, and it is observed whenever the source of waves is moving with respect to the observer. So when you have a source of sound and an observer, and one of the two of those is moving with respect to the other. So I'm just going to use this gizmo from explorelearning.com as a way to help you visualize what's happening and understand what's happening with the Doppler effect. So we have an observer in the middle of the screen. We have a vehicle moving towards the observer. And the first thing that I'm going to do is I'm going to play a sound sample, and that will provide an audio clip of what an EMS service sounds like as it's approaching, and hopefully you'll notice that the frequency appears to go up and then down as it goes past the observer. The second thing that I want you to look for is the successive wavelengths are represented by lines, and you'll also see the observed frequency in the top right of the screen, and the frequency will appear to increase as it approaches the observer and then decrease as it goes beyond the observer. And obviously the frequency, if it increases, then the wavelengths decrease, and vice versa. So I'm just going to play that, and hopefully you'll see. So now the sound is being emitted, the frequency is going up on the top right. As it approaches the observer, it's increasing. Those wavelengths are getting shorter. And now as the vehicle starts to move away from the observer hears that as a frequency which is lowering, and the wavelength is increasing. Okay, so what is happening? Maybe you can pause the video and have a think about what is happening in this particular photo, in this image. It is a bit of a wild image of that aircraft moving. And what's actually happening is we have a phenomenon called supersonic, or a sonic boom. It's very difficult, but it occurs because of something called the Doppler effect. On the image on the left, we have a moving source, which is the aircraft, and it is emitting a sound, and those wavelengths are shown by those circles. Think of something dropped into a pond or water, and those rings are being emitted outbound. The image in the middle is where the aircraft has matched the speed of sound, and that's called Mach 1. And so pressure starts to build up at the nose of the aircraft, and on the image on the right we can see that the aircraft is busting through the sound barrier, and so it's leaving a trail behind where those frequencies appear to decrease, or the wavelengths appear to increase on the left. Also, we can talk about what evidence that scientists have that the universe is expanding and we're part of this giant bubble. And, we sometimes call this, the remnants of the Big Bang, and we're part of this expanding universe. And the reasons for this are sometimes called the redshift pattern. So scientists theorize the Big Bang, or the expanding universe, because when astronomers look at galaxies, stars and so on over time, they see, and they use this tool called spectroscopy, and they look at emission lines, and those emission lines can be thought of as fingerprint patterns of the different elements of the universe. And what they expect to see is a certain fingerprint pattern where there are black lines at particular wavelengths for a certain element. In fact, what they see is at the bottom that for an element like helium or hydrogen or so on, that everything is shifted slightly to the right towards the red side of the spectrum. Now, on the red side of the spectrum, that correlates with longer wavelengths. So a lower frequency, longer wavelengths in terms of light. So if we think about this in terms of our sound principles, this could be matched up to a sound moving. So if the sound is moving to the right and we are positioned on the left, we would notice that as longer, longer wavelengths or lower frequency. And that would match up with that redshift pattern. So everything is moving towards a longer wavelength, lower frequency. In other words, the equivalent of the red side of the visible spectrum. And the opposite would be the case for things which are moving towards us. Astronomers theorize that things which are moving towards us would be shifted towards higher frequency, and therefore the blue or purple end, and that's called a blue shift pattern. So it can be used, the Doppler effect can be used to explain many things. We can also put some calculations to the Doppler effect. We can use an equation to relate the actual frequency to the apparent frequency. Remember that the Doppler effect is where there's an apparent frequency. The frequency appears to go up or down depending on the motion of the sound or the observer. And so there is an equation which is at the right side of the screen. That equation is different depending on whether the source is moving away from us, which is the top equation, or moving towards us, approaching us, which is the bottom equation. Now, the actual frequency is the frequency of source, and the apparent frequency is the frequency that the observer is going to observe. And we can see for a source approaching that this factor, which is the v here, is the velocity of sound, and the v source is the velocity of moving source. So it could be the vehicle which is moving at a certain velocity. And for the factor that's circled in red, the denominator is going to be less than the numerator. So what that means is that for a source approaching, the factor is going to be greater than 1, and so the frequency observed is going to appear to be greater than the frequency of the actual source. So I'm just going to leave you with a practice problem on screen, something to chew on, something to mull over, and something to practice. Hopefully this has been helpful, shining a light, pun absolutely intended, on the world of the Doppler effect, and you get an appreciation for how much it's used, and you get to practice some of the calculations associated with that. If you found this useful at all, then don't forget to give us a wee thumbs up and hit that subscription button.